I'm going to be going over this DIY frequency counter, which is measuring 100 hertz test signal at the moment. And I'm going to show the schematics of the entire thing. The DIY frequency counter circuit starts out with the most important part, which is the gate signal, the gating signal. This is a 1 second on, 1 second off, 0.5 hertz signal that allows the count of whatever you're oscillating, measuring, whatever oscillator you're measuring, to be exactly fit into 1 second. That way it gives you a reading of hertz. So the way the 555 timer is set up, it's set up as an astable multi-vibrator, but it has to be at a 0.5 or a 50% duty cycle. So the way to make a 1 second on, 1 second off signal with the 555 timer is to set it up this way. So pin 8 goes to VCC, pin 1 goes to ground, pin 3 is the output, and we'll talk about that after. Pin 4 goes to VCC, pin 5 through a 0.1 microfarad capacitor goes to ground. Pin 6 is tied to pin 2. Pin 6 and 2 are going to ground via a 10 microfarad electrolytic capacitor. Pin 6 further goes into this little network right here with diodes facing up and down and the resistors as shown. So the way this circuit works is when the capacitor is going to be charged, the voltage goes from VCC through this 100 kilo ohm resistor down through this pathway. It can't go here, so it goes here through the diode, and it passes through this 44.3 kilo ohm resistor. Now that's not a standard value. I basically combined several resistors in series to make this. And what happens is it goes, the total resistance here that it charges the capacitor through is 144.3 kilo ohms, and it goes down here and charges the capacitor. Once the capacitor is charged, then it's going to discharge, and so the path of discharge is from here, back up here, through this 44.3 kilo ohm resistor, through this diode, through this 100 kilo ohm resistor, and it passes to the discharge pin, which is pin 7. In this way, the charging resistance and the discharging resistance are equal, both 144.3K. So if you look at the formulas from the data sheet in the 555 timer, the T1, which is the charge time, is basically 0.693 times the resistance, which is R1 plus R2, which is 144.3K, times the 10 microfarad capacitor, and that equals to, if you calculate it out, about 1 second, 0.9999 seconds to be precise. Now T2, in a similar fashion, is the discharge, and that's 0.693 times R2 plus R3, which is ends up being exactly the same as the resistance for T1 because of this diode network, and then times the capacitance, which is 10 microfarad, and that's equal to 1 second. When you add up T1 and T2, the total time of the total period of the on-off cycle of the 555 timer is 2 seconds at a 50% duty cycle, which is equivalent to a 0.5 hertz signal. Okay, so now that output from the gating signal, which is from pin 3 of that 555 timer, 0.5 hertz. So that comes in here. Now the signal is pulled down when it's not on, so it's not floating, to ground through a 20K resistor. Okay, and this goes here. Now from here, you want it to serve as the gate for an input signal. So the way we do that is basically through a 1K resistor. This goes to the base of an NPN transistor. This is a 2N2222. Any real NPN transistor will work. The collector is open. This is where our input signal will come in. The signal that we're testing. You know, in the video that I had a 100 hertz test signal. But it could be anything from anything you want to measure, as long as it's configured to measure that. So from here, this is 22K or 20K resistor to ground, and then this is your output from this. So the output is going to the counter. In my case, I used a CD40110 counter. So for a CD40110 counter, it's a decade counter. It also is a 7-segment LED display driver. And obviously they're cascadable. They have a reset feature, so you can reset them with a positive going pulse. And they have a latch feature. So the output to the counter goes to the clock pin of the counter. Okay, so what that does is I'm going to draw one out. Basically, the clock pin is where this signal goes. Okay, now there's a reset pin and a latch pin also. Then there is a carry out pin. With the carry out pin, you can cascade this to the clock of another chip, and so on and so forth, for as many chips as you need, for as many displays as you want, for as many digits as you want. In my case, I used a 3-digit display, so that will give us a total of potentially 999 hertz signal that we could count, and anything from 1 hertz to 99 hertz. Basically, what we do with this signal is, by turning on this transistor, this allows the input signal to flow through. So it functions kind of like an AND gate, where you have the transistor or the gating signal, and it gives you a 1 second long pulse like that, and then you have the input signal, whatever that is. Let's say it's something like this, and what you get at the output is something that looks like this. So once that's done, however many are counted in here, that's how many are going to be count out and sent to the counters for the final count. Okay. What we do from this standpoint also is we have a separate signal that comes off of this area. And when this gating signal goes off, you get a downward edge, a falling edge of the signal. And this triggers the latch. And then this is attached to the latch of all of the ICs. And so what happens is the display is latched, so you don't see it counting. Finally, after it's latched, we want a slight delay, and after that slight delay, we want to be able to reset these pins so that after the display is latched and we could see the reading, then we want to reset that. So how do we do that? We do that with basically a capacitor, and I used a small capacitor, 0.1 microfarads, and then I have a resistor going to ground here. This is a 1K resistor, and basically from this signal we get the reset, which goes, and it's a little bit of a web here, to the reset, and it resets all of them. So in this way, we have our 7-segment displays displaying the total count that's in here. That count is latched, so we don't see it counting, and every 1 second, according to the gating signal, we get a brand new fresh latched display of the fresh count. So like I said, this signal, based on the number of ICs you use, cascaded together, that'll give you how high of a frequency you can count. So in my case, I could count to 999. Obviously, you could count to 10,000 if you add one more, 100,000, et cetera, et cetera, et cetera. So this gives us, that's the beauty of this particular chip, as opposed to the CD4026, which is also a decade counter and display driver, but it does not have the ability to latch. And so that is the downfall with that IC for the purposes of my project. And so since it doesn't latch, you just basically see it counting the whole time. And so it never really fixates on one value. So it's constantly counting. So in any case, that is the entire circuit. And I'll show you what it looks like on a perf board. And I hope you guys like it, and I hope let me know if I did anything that you guys would have done differently. But thanks for watching.